Gabriela González, former spokesperson for the LIGO scientific collaboration from LSU, is going to tell us about how to hear black holes and other cosmic sounds.
Thank you. Can you hear me? I guess so. Yes, so I want to tell you the technical details, not just the detections we have made, which I presume you have heard about, but also the technical details, how Harija said it yesterday, how the sausage is made. Because sometimes people stop reading or only read the figures and the captions, or figure 1 and the caption of figure 1, but there's a lot more in the papers, and that's why you should believe us. First of all, let me say that whenever I say we, it's the LIGO scientific collaboration and the Virgo collaboration. We do the analysis of the LIGO data together, and we will do the analysis of LIGO and Virgo data together. And we are a team of more than 1,000 people, and we really work together. So this is a plot that you might have seen, and I wanted to take a few seconds to show you what it really means. This is how we represent the noise, and this is the best noise curve that we got in the initial LIGO era. That was in around 2010. And what this represents is how small a strain we can measure on the y-axis versus the frequency at which we can measure the strain. And you might remember that strain is fractional change in distance. In these interferometers is the difference in distance between the two 4 kilometers divided by 4 kilometers. So you see these very small numbers in here, 10 to the minus 21, 22, 23, and you would say, well, that's much better than the 10 to the minus 21 that you always advertised. But that's because this is a density, this is a strain noise per square root of hertz. In power, it's a density per hertz, and you need to integrate it over your best sensitive band. You have to decide what is the band that you want to integrate on, and that depends on what gravitational waves are you looking for. And then if you integrate, for example, in here in our sweet spot, then you get that 10 to the minus 21. It's the RMS noise that you have to compare with signals. We can do better than that. I don't know what happened there. We can do better than that by matched filtering, but this is a way to represent our noise model independent. The other thing we can do with a noise curve is translate it into sensitivity to a given source. And the metric that we have been using, and we still like a lot, is how far away could we see the coalescence of two neutron stars with a signal-to-noise ratio of 8. And we will talk more about signal-to-noise ratios later. So this curve that we had again in 2010 had a range of about 20 megaparsecs at best. We had between 15 and 20 megaparsecs in the last science run in 2009 and 10. So that's what we had, and this is what we want to have. This is the advanced LIGO design curve. That's how good we can get if we make everything work the way we want it to work, which is a lot more difficult than it sounds. And if we get here, of course, this is 10 or 100 or 1,000 times better, depending on what frequency you look at, then we could see binary neutron star coalescences up to 200 megaparsecs away. In fact, we can see them farther if they are optimally aligned to us. So how do we do this? Well, in general, at low frequencies, we are limited by seismic noise. So between initial LIGO and advanced LIGO, we now use better seismic isolation. At middle frequencies, we are limited fundamentally by Brownian motion, the fact that we are working at room temperatures, atoms are moving around, and that limits the sensitivity to our strain. And the amount of Brownian motion at each frequency depends on the energy losses we have in the system. So we have reduced the Brownian motion not by reducing temperature, but by reducing the sources of losses in our system. And at high frequencies, we are limited by the quantum noise in the laser light that we use, and that's the uncertainty in counting photons. That's 1 over square root of the number of photons, so we use more photons. We use higher power. So if we get all of that working together, then we will get here to 200 megaparsecs. We are not there yet. Now let me show you, and I could spend the whole talk talking about this. Let me show you a few of the pictures. I know that, I think that there are no experimentalists here. Although, yes, Karsten, I'm sorry. And I heard some people have some experimental experience in their younger years. But this is an engineering and physics marvel. We really get to the fundamental noise limits that all this structure, huge structure, can get. So these are 4 kilometers in vacuum. This is vacuum tubes that have a meter, 1.2 meters in diameter. This is high quality vacuum. We have quadruple suspensions as opposed to simple suspensions that we had in LIGO. These suspensions have nothing attached to them, and they are hanging on monolithically glued glass fibers, and that's how we reduce the losses and the Brownian motion. All of this quadruple pendulum is hanging from a seismic isolation system, which is active. We measure the relative displacement between the layers, and we cancel it. All of those things are inside vacuum tubes. We have a high-power laser, and notice that this advanced LIGO detector, as opposed to the initial LIGO detectors, has hardware that was not just funded by the National Science Foundation, but also by European agencies like STFC and the Max Planck. So this is truly an international collaboration in many different ways. Now, the interferometer that we have is also not a simple interferometer like I like to show in public lectures. It's actually, it has Fabry-Perot cavities in the arms. We operate it on the dark port, meaning that we have destructive interference at the output, which means that we have constructive interference going back to the laser. So we put another mirror in here to form another Fabry-Perot cavity with this considered as a mirror. So this is a Fabry-Perot-Michelson. This is a power recycled Fabry-Perot-Michelson. And in advanced LIGO, something we didn't have in initial LIGO, is we put another mirror at the output to recycle the signal if it comes out. So this is a dual recycled Fabry-Perot-Michelson. We have to use all of these to get noisy data. It's not that we get zero, and then when a gravitational wave comes, we see something. We always see something, and then we have to dig in that noise to look at the signal, to find the signal. So this is where we were. This is the explanation of the noise curve we had in Hanford and Livingston, the two LIGO detectors, 3,000 kilometers away, in 2015. And this is not quite at the advanced LIGO sensitivity. I told you that that one will have 200 megaparsecs binary neutron star range. This one had about 70, 75, 80 on a good day. So we still have a way to go. But we had decided, actually, even more than a year before this, that when we got to this sensitivity, we would take data for a few months so that this is not a gravitational wave signal. This is my insulin pump. So we would take data for a few months. We didn't have any expectation of detecting neutron stars because the sensitivity, we think that we need at least 150 megaparsecs and quite a few months of data to see that. But perhaps we were going to have interesting null results because there were very optimistic black hole theories. We could touch perhaps some of the neutron star rates. So we had decided beforehand that we were going to take a few months of data, even though we were not quite at the 200 megaparsecs range. So this is what we had. We were not using the 200 watts that we have in the laser. It turns out that using high power complicates everything. So we are turning it up slowly. So we are only using 20 watts. That, even with that, you still have 100 kilowatts of laser light heating and circulating in these cavities. So this is a huge, huge deal. And this was September 2015. As you all know, in September 14, we saw this. Now, this is amazing. This is not the way we first saw it, and Bruce might tell you more, but what we have is algorithms that are running on the data telling us whether there is an interesting trigger, and if there is an interesting trigger, whether there is one in coincidence with the other detector. And that is what appeared on a computer. We were not taking data in observing mode, so we were not taking data 24/7, but we were testing everything, in particular, these detection algorithms. So a student, a postdoc actually, and Bruce is going to tell more about that story, saw this trigger and said, who put that there? Because it was very loud. And then he plotted it in time frequency, and you could see it clearly. It was only later that we filtered it, and we came up with this nice, but now we have realized that it might have led to some misunderstanding. But what we are showing in here is not the way we analyze the data, but it is the way we were so impressed about this data. So what I'm showing here in blue is the output in the photodetector, in the Livingston detector, calibrated in strain, and with some minimal filtering. We are using a bandpass filter, and we are notching lines in here. So it has some filtering in there. This is noise. That is noise, the normal noise that we see in the detector. But then here you see, by eye, a sine wave that grows in amplitude and frequency and then decays. And as you saw from the numerical relativity simulations, that looks very much like this simple coalescence of black holes. And then the Hanford data, if you shift it by 7 milliseconds, then you see that it agrees quite well. So this was the coalescence of black holes. And you can tell, and Bruce is going to tell you more about that, you can derive some of the parameters even from this figure if you just look at the frequency and the time scale to look at the frequency of these cycles. You can convince yourselves that these are black holes and not neutron stars, for example. But this is not how we do the analysis. Before getting to the details, let me remind you that that was not the only thing we saw. We saw that in September. We got prepared to take data 24/7. That this happened on a Monday. By the next Monday, we were taking data 24/7. We put everything on track. We took data for 4 months. We saw another big detection on December 26. December 25, Christmas in the US. It was still Christmas in the US. We saw a candidate in October. So we had 2 good signals and 1, well, I'll show you the details of that third signal and let you decide. But we analyzed all of this data very carefully. And we stopped in January. As I said, we had a range between 65 and 80 megaparsecs. We didn't, you have heard more about that, but not as many more detections because we took quite a few months to work on the detectors. We still want to get them to that 200 megaparsec sensitivity that we want. We have a lot of work to do. So we did some of that in here. And we started taking data again on November 30th, and we have a range between 60 and 100 megaparsecs. And if you ask me later, I can tell you more why that 60 is less than that 65. But what you should look is that 100 is larger than that 80. So, so we know better things, even though the 2 detectors don't have 100 megaparsec sensitivity. We have progressed in our understanding of the instrument. And that's very good. And the other good news is that Virgo is ready to join us any minute. We are waiting any time for them to join this run. So we will stop in August, but perhaps we will take a month or a couple of months of data together. And with any luck, we'll have a detection for which we can do some localization. Now, these are the 3 papers that you probably remember that we have published. The first observation, the December observation, and the more recent January observation. We saw a gravitational wave on January 4th during this run, and we have done the analysis of the data around that detection, and we have published that already. Notice that we have not waited until In the beginning, we thought that we would wait until the end of the run and publish everything we had. We said, well, maybe that's too long to wait, so we published this. But we have done quite a bit more of this. We have published a paper with the full analysis for binary black holes in O1, and I will show some plots from that. We have searched for short gravitational bursts, and there was one burst found, and that was the September 14 event. But we have looked for other bursts, and we have not found anything. We have looked for a stochastic gravitational wave background, that is, from correlations in the data between the Hanford and Livingston data. And we have not found anything, and we have published upper limits from that. We have looked for binary neutron stars and neutron star black hole mergers, and we have not found any. We didn't expect any, but that allows us to put better upper limits than we had before. And we have looked for known pulsars with advanced LIGO. These are periodic signals from pulsars that we know the position on, the sky position on, and we have published that. But we have several other searches going on. For example, the searches for unknown pulsars, the broadband search, and results are close to come out, right? Yes. So we do a lot of searches. We don't do just binary black holes. Now, black holes is what we found, and you can see that we are really doing astronomy. This is what we knew about masses from X-ray studies, and the first one was a big whopper, and we have to thank nature for that. I have no idea how nature decided that we deserved such a nice signal as our first signal, but there it is. So both original black holes and the merger one are, of course, larger than all the previous ones. The second one was a normal one, if you want, but remember, this is a binary black hole system. It's the first time that we saw two black holes merging. Because they're black, we cannot see them. We don't expect to see them with electromagnetic waves, but here we can see that merger. This is a candidate in between, and this is a January detection close to the parameters of that candidate. But this one is quite a bit farther away. These are at redshift of 0.1. This is a redshift of 0.2. So it's quite a bit farther away. So back to the sausage. This is figure 1, and we put it there. We produced it just for the plot, actually. These are not figures that we produced as intermediate steps in our analysis. But we couldn't resist, because they're beautiful. I explained already what this is. It's a superposition of the filter data in the two detectors. Harold explained what this is. This is a numerical relativity, the template, and the reconstructed wavelet. So you can reconstruct the waveform even not assuming that you have a model for it, and you get about the same. This is a residual that you get subtracting that from that. And when we produce this plot, we looked at that residual and we said, yeah, that looks like normal noise. But we never use this kind of residual data for doing our analysis. And we see this beautiful time frequency pattern that, again, we only use in general for diagnostics of bad things in the data, not for looking for waveform. But again, this is beautifully showing that there is a black hole in the data. But the actual search is done with matched filtering. And this is a very well-known statistical technique that assumes that if you have a waveform in the data, which is smaller, it might be smaller in the data, so you don't see it. The RMS is smaller, you don't see it in the time series. Even if you try filtering, you wouldn't see it cleanly. But there is something in there. You think that there's something in there, and you think you have a good model for it. Then you use your model, you use your waveform model, and then you cross-correlate that waveform model with your data at different times. And from that cross-correlation, you define something that we call a signal-to-noise ratio. And the signal-to-noise ratio is not 0 if the signal is not there. It's just a random number. So let me show you this simulation. So you get a random number in here, and when the model matches the actual signal in the data, if you have a good model for that signal, then you have a peak that is not consistent with the noise distribution of this random noise. Now, there are several problems with this. It looks in here that it's an easy way to find a signal. Problem is that, of course, we are looking for binaries of all sorts, black holes, neutron stars, but also of all sorts of parameters, and we have to do this in the whole data, so that is actually a very expensive proposition. But also, if you do this on not simulated data, but actual data, and you do it for not for 10 seconds, but for an hour, then you see lots and lots and lots of peaks for lots and lots and lots of models. Our noise is far, far, far from what you expect from a Gaussian distribution. So if you do this analysis on the data from one detector, you would think that you found lots and lots of gravitational waves. But we know those are not gravitational waves because when we do the same thing in the other detector, we don't see the same thing. Sometimes we don't see a peak. Sometimes we see a peak of different magnitude, but for different models. So the way we decide that there's something worth looking at is if we have matches with models in two detectors within a reasonable time window. We have a 10 milliseconds, but we extend that to account for uncertainties, and with the same models, with the same masses if you are talking about a binary system. So the coincidence is a very, very powerful test. And for the second detection, for the December 26th detection, you probably looked at the paper and you didn't see such a nice time series as you saw in the first one, but we have it there. This is a similar plot. It's, I always forget to correct these. These are, I think, something like 10 seconds in here. A second, it's quite a bit longer. The red is the time series with the signal in there. We have not subtracted anything. And this is Livingston, and this is Hanford. You don't see anything in there. In fact, what you see is this black waveform in here, which is what we found. This is a model that matched our data, and we plot it on top of it, so you can say, well, there is something in there, but I didn't expect to see it. So there isn't such a beautiful plot that we can use to convince you. But this is a way to convince you and everybody, is that when you plot the signal to noise ratio time series, then you have a big peak, a large peak here in Hanford and in Livingston. And when you look at these figures, sometimes people ask, but that's smaller than that. Is that the same model? Yes, it is the same model with the same amplitude in both detectors, but the noise in the detectors is slightly different, so you don't expect the signal to noise ratio being the same. The signal is the same, but the noise is not. So the signal to noise ratio is different in both detectors. So in the analysis of all of O1, we found these three signals, or two signals and a candidate. So this was near the edge of our bank. The masses were quite high. The September 14, this was a December 26, lower masses. And here we have two symbols for this candidate, and that's because we have two different methods to look for these signals, and the two methods found a slightly different waveform for each of these. This is not how we estimate the parameters of the signal. This is how we find the signal. We use a sparse, what numerical relativity people would call a sparse template, because we cannot do a very finely spaced template to know the parameters. So we have, once we know there's a signal there, we throw at it thousands and thousands and thousands, tens of thousands of waveforms to see how good the match is. Now, before I get to parameter estimation, let me tell you about the confidence on the detection. So that's the detection without reference to parameters. This is a signal-to-noise ratio combined from the two detectors that we had for September 14 event. It was more than 22. It was huge. Now, the question is, how often can you see that by chance in the instruments? The problem is that you cannot estimate that assuming that you have Gaussian noise, because we know we don't. You cannot calculate that by shielding your detector from signals, because you can't. So the way we do it is we look for coincidences in the signals, applying a time shift between the signals. So we shift the data by 10 seconds, and then we use the same method to look for coincidences. Any coincidence that we find will be a false alarm, because there can't be an astrophysical signal that takes 10 seconds from one detector to the other. So this is the histogram. This is one signal one event that we saw at this signal-to-noise ratio. This is a histogram of the number of events that we saw at the different signal-to-noise ratio amplitudes. Of course, these are fractions because we did millions of time shifts. So this, in a million time shifts, we saw a few of this amplitude. We saw nothing like this amplitude. So this tells you that this has a confidence of about 1 in 200,000 years. And that you are extrapolating because you don't see anything here, so you are extrapolating from this. But on top of that, when you look at this and you say this has a very strange shape, so what are these spurious coincidences, they all turn out to be the big signal in one detector with some noise in the other. So now if you snip out the data in the two detectors and then you do the histogram again, you don't see anything larger than 13. So that's a huge significance. And that's the histogram that you can use to look at the significance of December 26. Even compared with this histogram, it would be very significant. But when compared to this, it's even more significant. So this is also what you would call a 5 sigma event. Although I don't like sigmas because those assume we have a Gaussian distribution and we don't. So this was very significant. This is the other event, the candidate, the third loudest candidate. And if you calculate the false alarm rate, it's 1 every 2 years. Now that's what we experimentalists say. My theorist colleagues say, but that means it has an 85% of being real and a 15% chance of being noise. You decide. Now, I was saying to find the parameters, we have to do a lot more work. We don't find the signal. Now we find the signal, we have the time, so we have rough estimates of the masses, the parameters, so we throw thousands and thousands of approximate waveforms, these modeled waveforms that Harold was talking about. And then these waveforms have 15 different parameters if you include spins, and every parameter will marginalize over only a couple, like the time and the phase. And then we project them in the different parameter spaces. So this is the mass parameters, the two initial masses in the black hole. And this is a 90% contour for the January 4th event. And here you can see the contour for the September 14. The December, notice how thin one this is. It gets thinner, which means that you have an estimate of the chirp mass, which is in this direction, much better because it is much longer. Lower masses means a longer signal. But when you project it over the masses, which is what you really want to know, the uncertainty is quite big. So when we quote median values and uncertainties, we quote this estimate, which is a 90% credible interval, and the median value. This is a Bayesian estimate, so in these plots you see the priors and then the convergence of two different families in here. And it's all very consistent. So this is how we estimate the masses. Like I said, there are many different parameters. This is how we estimate the final mass and the spin. And this is one of the reasons why we cannot prove the area theorem, all these waveforms, all these families are assuming GR, and even assuming GR, you get these very large uncertainties. This is the uncertainty. This is the plot for distance and orbital inclination. All these parameters are coupled to each other. These pairs are the ones that are most strongly coupled to each other. This is a sky localization, which for 2 detectors is, of course, very, very small. Spin is one interesting parameter, but it's actually the one that's probably the most difficult to do. So for estimating the spins of the individual black holes before the merger, we have these plots that it took me a long while to understand, so I don't pretend you will understand them just from seeing here if you haven't seen these before. These are for September 14 candidate, the October candidate, and the December data, the December event. Look, this is the one that has the strongest contrast in colors, which means that it is the one for which we can estimate something. And the estimate is on this direction is the magnitude of the spin, and on this direction is the direction of the spin for the primary mass and the secondary mass. So you can see that there is something in here. If you look at the contour, what we do is we estimate the effective spin. This is the spin projected on the angular momentum direction, weighted by the mass, but the masses are similar to each other. And again, you have a contour in this case versus the mass ratio. And for December 26 seems to be away from 0. But it includes 0, so it's not so amazing. The thing that to me was most interesting about these things is that these are not large spins. These are large black holes, but they are not large spins. Of course, the final spin is larger, it's 0.6, but that's because that's the spin of the angular, from the angular momentum in the orbit. The January event that we just published is also quite interesting. If you look at spin, here is a projection, again, of the effective spin along the angular momentum direction, and this is what we call the precession spin. This is projected over the orbit, and that would determine the precession of the orbit. And this one, we don't get to anything. I mean, almost every magnitude is consistent with it. For this one, we get something close to 0 for September. For the others, for this January one, it looks like it's negative. Of course, the median value is negative. The 90% credible interval comfortably includes 0. But again, you can draw interesting conclusions there if you want to. This is a reason why we like to plot these. You probably cannot see it here, but we have an artist's depiction of this coalescence with the orbits of these 2 black holes away from each other. Okay, so when you read tables like these, you have to think about the plots, you have to think about the parameter estimation techniques that we do. It's a lot of work. We can also test GR, and I won't have time to describe this, except to say that we do this at converting it into post-Newtonian orders. Harald talked a bit about what those post-Newtonian orders, it's not exactly the same, but it's the same idea. And what's shown in here is that for the lowest post-Newtonian order, we have much, much better tests at the percent level from binary pulsar systems. But we have the first tests at the order of magnitude level, so they're not very precise, for higher post-Newtonian systems. That gets better when the best limits that we get are from the December event. Bruce will talk more about this, but this is trying to estimate independently initial masses and final masses. In this case, we are doing this using GR for fitting the initial part of the waveform or for fitting the final part of the waveform. And again, the uncertainties that we have on the final mass and spin are much, much larger than before. This is the uncertainties we had, assuming GR for the whole thing. This is assuming GR for post-inspiral or the inspiral part, and these uncertainties are too large to draw any conclusion. So what's the future? In the 0 minutes I have, it's very exciting. this is the data we have taken. We have not finished yet. We'll finish in August. We'll take about a year down to improve the sensitivity. We think that we will get to, I hope, more than 120, perhaps 150 megaparsecs. If we get there, we might see neutron stars in that next run, but our target is 200 megaparsecs, so we still have a ways to go. And this is the advanced LIGO era. There is also the other detectors. There's Virgo, there's Kagra, there's LIGO India. Those are all advanced LIGO technologies or advanced LIGO sensitivity kinds. So we will have a network of detectors, which means more detectors, better localized detections. We have ideas on how to build better detectors at current facilities and in new facilities. We just need the money to do it. So if you have the people willing to bet, maybe we can use that. And we have, again, not just black holes. We are waiting to hear lots and lots of different nodes, not just from our searches in our detectors, in ground-based detectors, but from other gravitational wave technologies. So going back to the title of my talk, these are just the first few notes, and while I take questions or people think about questions, I can't resist but playing this again, which is first that minimally filtered data without any change in frequency. It just sounds like a thump. It's low frequency, 100, 200 hertz. And this is our false color, false frequency. We added 400 frequencies. To make it sound this nice. So that's a symphony, the first two notes. Thank you.
Gary has a question.
Is the main source of the uncertainty in estimating the masses of the black holes theoretical or experimental? I mean, do you know? I mean, if you could do perfect numerical relativity instantaneously, would those errors shrink tremendously?
I don't think so. I think that, perhaps Neil can say it more, but I think the errors, the uncertainty is determined by how loud the signal is compared to the noise. On top of that, we have at least a few percent uncertainty in calibration, so that is marginalized in there too. But
it's more experimental, I see.
Yes, Gary.
I believe that there are, I've seen a paper in which people try to estimate from the lack of dispersion in the signal that some bound on the mass of the graviton. Is that true? And if so, what are the values? Have you looked for that kind of thing?
Yes, we have. It is in our papers. We have a test of GR paper on the first detection, and then on the December detection. And there is a paragraph, and that's the one about the dispersion in this January detection. I don't have the values off the top of my head, but I can send you the references.
Okay, thank you.
They're not earth-shattering, but they are good. We can test GR.
Right here.
Thank you. Regarding the waveforms that you use for the matched filtering, are there any waveforms that exist and that maybe are used that are waveforms from alternative theories of gravity, like Brown-Sticky waveforms that have an extra scalar mode?
When the first detection came, of course, the first one of the things that we wanted to do was test GR, and we did this analysis in here, and then we said, well, we should look for waveforms from alternative theories. And we didn't find any. And I think the explanation is that, like Harold and Pablo said, that calculating waveforms from any theory, including GR, on which you have lots of people doing theory and numerical relativity, it's very, very hard. Right. But I wish we had some, yes, especially families of waveforms.
Yeah. Thank you.
Just a comment on that. Of course, in Brown-Sticky and most scalar tensor theories, it would be the same, because this is vacuum black hole without matter. So because thanks to the O'Hare theorems, the black hole vacuum waveforms won't differ. There are, of course, other modified theories of gravity where they would differ, but for Brand-Sticky that you mentioned, you couldn't see the difference. You need matter. You need something to circumvent the no-hair theorems of black holes to have differences in the waveforms.
Yeah. Okay. There's a question up the back, and as you take the microphone up, it's worth noting that the first signal we detected with no waveforms, so if it had been from alternative gravity, we still would have detected it because we were able to detect it without any waveforms. It was high confidence in the burst searches. Yes, up the back.
Okay. Did I hear you correctly that you said within the range, the statistical range of possible spins, it included negative spins?
The median value for the January 4th detection is a negative value. But the 90% credible interval comfortably includes 0.
But what do you mean by negative? Is that something that would be...
Oh, that means that the spin of the initial black holes, again, projected on the orbital angular momentum, are in opposite directions from the angular momentum.
Okay, thanks. I guess I also wanted to ask, if I may, when you say you assume general relativity when you do your statistical analysis, does that include that you assume, for example, when you're looking at your distributions, possible ranges for the masses, do you include an assumption that Stevens' area theorem holds?
Yes. I mean, that's a theorem proven using general relativity, so we use general relativity, so that assumes all the consequences of general relativity. Okay. Yes.
All right, one
That's
last
why
question
it's not a proof of the area
from
theorem.
Bernard here, and then we'll need to move on so we can get to lunch.
Obviously, it's very exciting that these black holes are so big, and some people have even speculated that they could be primordial black holes. But I would like to ask you, is there any prospect of detecting them if they were actually very small, if they were less than 1 solar mass? Because in that case, they really would have to be something more exotic like primordial black holes, which would be a nice birthday present for Stephen.
Yes. Actually, that is a search we have done in the past. We have not finished it yet for this advanced LIGO data. It's not... We probably would, if it was strong enough to be a detection, we would have seen it with the model-independent methods that we have. So we could look for binary black holes, digging deeper in the data, but then it would be a weak data, it would be a weak signal, and we probably wouldn't be able to conclude much from it.
But it's not excluded yet?
It's not, well, we did, no, it's not excluded below 1 solar mass. I think people might correct me, but I think we had a 1 solar mass bound on our neutron star searches. Yes.
Thank you.
Yeah.
Well, that's what I'm asking. Was it 1 or 0.5? I think it was 1. But it gets more computationally more and more expensive as we go down. So if you ask me, I think we would wait for a burst detection, which means there is something there, and then we would look in there to see what that was. And we have not found anything with burst searches.
All right, well, let's thank Gabby for a very interesting talk.